at 3:25, ready to kick off the next segment of the geological characterization session. For our first talk, I'd like to introduce Charles Logan from the GSC to give our next presentation. So Charles, you can go ahead and share your screen whenever you're ready.
Okay. You see that? Oh, wrong one, eh?
Yeah. Just see your presenter's view.
How's that?
Perfect.
Great. Okay, hi, my name is Charles Logan. I'm a 3D geomodeling specialist with the GSC. And for the last 8 years, the bulk of my time has been spent developing 3D models for Southern Ontario. Let's see. All right. This will be a high-level overview of the modeling process, and the goals will be to compare and contrast regional superficial and bedrock models of Southern Ontario, with a focus on modeling strategies based on geologic complexity and the data support. Laser pointer here, there we go. This effort has been a collaboration between multiple agencies and a large number of contributors that have provided essential geoscience guidance and technical support. Hayes and Russell and Terry Carter are the project leads and my co-authors. We have developed 2 regional models of Southern Ontario. The bedrock model consists of a lithostratigraphic version and hydrostrat version. Covers 110,000 square kilometers. Secondly, the superficial geologic model covers a smaller 67,000 square kilometer area, excluding the Great Lakes. The models were developed using Leapfrog geomodeling software. And to better understand the modeling strategies used, it's important to understand how Leapfrog works. Primarily, surfaces are estimated using borehole contacts and 3D vector objects, and structural data can augment this. And then volumes are defined between successive surfaces based on the defined chronology and the type of surface. Surfaces can be deposit, erosion, intrusion, or veins. However, for sedimentary lithology, we use deposit or erosion only. And this example is relatively simple with continuous layers. With more complex geology, layers are not continuous and surfaces overlap. The type of contact surface dictates how the volume is constructed. At location A, both overlapping surfaces are depositional. In this case, the older volume is unaffected by the younger surface, and we have an overlapping scenario. At location B, the younger overlapping surface is erosional. It removes the older volume. This example illustrates the impact of borehole contacts versus vector objects when used to control surfaces. An added vector point will only affect the interpolation of the corresponding surface. It will not affect the interpolation of older surfaces or older layer volumes. This is the same contact added as a depth from to borehole with a partial depth bottom interval. In this case, the older surface interpolations will actively avoid the younger depth interval, and thus the older layer volume is suppressed. This actual model example shows a surface interpolation adhering to primary lithology in red, and also avoiding younger lithology in blue if the depth warrants it. Note that boreholes are more computationally intensive than vector contact points. So on to the models of Southern Ontario. So to answer the question, is there adequate data support to develop a 3D model? The answer depends on the data, density and quality, the geologic complexity, and the goals of the model. Summary of the bedrock model situation. So we had the good fortune of having a single source of relatively clean and expert interpreted borehole logs from the oil, gas, salt resources library. So the coverage changes from pretty good to pretty poor to the east. The formations of the Michigan Basin are generally consistent over large areas, and most formations occur where the data coverage is good. So for regional contexts, this level of data support was sufficient. The exact opposite. This is a summary of the superficial model. The subsurface data was compiled from several sources, and it varied greatly in accuracy and geoscience content. The aerial coverage overall was better. However, the vast majority was inaccurate water well logs and not interpreted for stratigraphy. The geologic complexity is higher. There are more discontinuities and increased surface variability and thickness variability. So for regional context, data support was marginal and needed more guidance and intervention in the form of expert feedback, manual edits, and ancillary data. Excuse me. So to build 3D models, we first construct a 2-layer model of generic overburden and undifferentiated bedrock. Using the generic volumes as 3D boundaries, the final models are developed within. And doing this makes it much easier to truncate layers at the bedrock surface. To help mitigate data gaps, we use 2D geology mapping coupled with a topographic DEM to augment the subsurface data. So to do this, a grid of points is overlain on the digital geology, and it's tagged with both the geology code and the topographic elevation. The geology map grid points can be used in 2 ways, directly as vector points or converted to pseudo borehole collars with related depth intervals of 1 meter. By using them as pseudo boreholes, we leverage the avoidance deflection feature we saw earlier. A 1 kilometer grid of pseudo boreholes was added to both models. But because of the higher complexity, an additional grid of 500 meters spaced, less computationally demanding vector points was added to the superficial model. So overall, the regional model strategy after data prep is we standardize all data to topo DEM and model layer codes where possible. We then begin an iterative cycle of model building. So we develop a model, we inspect it, and then we revise it and correct the data and repeat as needed. After the data revision, automated data anomaly checks are done to identify possible errors before data is reloaded into the modeling software and reprocessed. 2 types of anomalies are detected: elevation spikes and overly thick intervals. So to do this, we use a moving window centered on each borehole in turn to select a subset of comparison boreholes within a given range. Within the selected subset, a local average thickness and elevation is determined. Simple stats are then used to flag potential elevation and thickness anomalies by comparing the test thickness and elevation to the subset averages. So this is automated and done for every contact and for each tested layer. Pretty time consuming. This is a summary of the lithostrat model. I won't go into the details given the time, but in particular, there are 53 model layers and quite a large number of contact picks that are pre-coded by geoscientists. This is the data distribution of boreholes. See that it's concentrated to the southwest. And as they're supplied by the OGSR library, they reflect the patterns of petroleum and salt exploration in southern Ontario. So to develop the lithostrat bedrock model, as mentioned, we use the generic bedrock volume as a 3D container, then borehole contacts, along with pseudo boreholes and 3D P-line edits help to control the surfaces. The P-line edits are used to maintain layer thickness where data is sparse and to help form the proper shape of layers when truncated at lateral model boundaries and model surface boundaries. The interpolated surfaces initially extend beyond the model boundaries. But when layer volumes are developed, they are truncated at the 3D boundary. Layers are developed from oldest to youngest using upper contacts. And just to note that all bedrock surfaces were developed as depositional type. So the publication includes the lithostrat layers, fault planes, hydrocarbon storage and solution mine caverns, and we had 2 salt mine volumes developed. A summary of the hydrostrat model, it's the same volume and area, but in particular, there are 15 modeled layers or hydrostratigraphic units, and they are derived from merging lithostrat bedrock model layers. The model consists of 15 hydrostrat units called superficial sediment, aquiclude, aquifer, aquitard. We have fluid zones within the aquifer defined by interpolating within the volume. We developed static water levels for the aquifers. And we did a total dissolved solid for the Guelph aquifer by doing another 3D point interpolation within the Guelph HSU. We have inferred karst zones that are based on freshwater depth into bedrock. And we also include 3D rendered petroleum pools and petroleum borehole occurrences in borehole logs. This is a summary of the superficial model. Again, I'm not going to go into the details, but there are 7 modeled layers, very large number of material intervals, and very importantly, they're mostly not interpreted stratigraphically. The data are more evenly distributed and more dense than the bedrock model data. And we also utilize digitized GSE seismic profiles and the gridded surfaces of published OGS models. Data preparation was a very large part of the superficial modeling process. Data required standardization and air vetting for the provincial water wells that have well-known accuracy issues. But most importantly, to note, materials must be classified into stratigraphic model layers. The subsurface data sources were grouped into 3 classes based on accuracy and geologic content. Class 1 are the widespread water wells. They are not accurate and contain no geologic coding, just material textures. Class 2 is accurately logged and located, but it's also without geologic interpretation. And they're also often clustered in local studies. Class 3 data is both accurate and interpreted by geologists. It's important to note that all of the bedrock data would fall into this class. Interpolated surfaces were snapped to class 2 and 3 data, but not class 1 to limit the effect of data noise. Because the majority of the superficial data was not coded stratigraphically, the surface modeling process involves several iterations of semi-automated data coding, anomaly checking, model evaluation, and data correction. A semi-automated rules-based expert system was used to help code roughly 300,000 class 1 and 2 boreholes. So this process first involved developing a preliminary framework model based on class 3 data that includes the 2D map geology grid points. Class 1 and 2 boreholes were then tagged with surface geology, distance to class 3 data, and the depths to all framework surfaces. A code is then auto-assigned if the uppermost material is typical of the map geology, subsequent materials are consistent, or if class 3 data is nearby and material type and depth agree with framework surfaces. So that means a typical material and it's within an elevation tolerance. Screen depths are also used to help confirm aquifer formations. After automated coding steps, the data is visualized in 3D context with the 2D map geology and class 3 data. The preliminary coded intervals are examined in a series of cross sections. Errors are identified visually, and bulk selection and recoding tools are used to correct populations of miscoded log intervals. Uncoded log intervals are also identified and coded where possible based on context. And so after multiple iterations, we get to the final model. We improved from approximately 40% auto-coded initially to approximately 80% coded for the final model. And note that all surface types are depositional except for the regional till that was erosional. A regional till is a regional unconformity. It's dissected by incised channels that are better rendered when using the erosional surface type. Also, manual vector edits were used to help control model layers where seismic profiles or expert knowledge warranted, notably along tunnel channels. So the superficial model has just recently been completed and is in the publication process. It should be ready for download and viewing within weeks, hopefully, through the NRCan's new Open SMT repository, formerly GeoScan. And so here's a sneak peek at the main superficial layers. This is lower sediment, regional till, glaciofluvial sediment, and what we call post-regional till mud. There are currently no plans to develop a hydrostat version, but this may change, one never knows. These are some examples of products developed to increase outreach. We have video presentations by Terry Carter and the OGSR that can be viewed on YouTube for more geoscience content related to modeling. We have virtual reality, augmented reality animations, and 3D printed models that were developed by the OGSR. The digital model is freely available to download and viewable through the Leapfrog viewer that you can download for free. And we're currently in a collaboration with the Polish Geological Institute to serve the hydrostat model online via Geo 3D. In addition to the impacts of the bedrock model mentioned by Hazen and Helen earlier today, these are some studies related to Southern Ontario modeling. Confidence assessment of the bedrock model by Melissa Bunn et al. An interesting study involving the 3D interpolation of dolomite percent within lithologic layers by Terry Carter et al. And as a segue to the next talk, a current study is underway that's supported by an attempt to model the Thorncliffe Formation within the lower sediment superficial model layer by David Sharp et al. I guess that's it for me. Thanks very much.
Thank you, Charles.